Okay, so what I'm going to talk now is about the routing functionality in the GFS, and basically under the GFS frame processor. That probably you heard about it. Now, NBase envisions the Ethernet as a network of choice covering the LAN, the campus, and in some cases the metropolitan area network and the wide area network. Basically, we have the first two probably are obvious, the LAN and the campus. We have today installations using our fiber optic technology that span over hundreds of kilometers, basically implementing metropolitan area network, and we can even call it a wide area network. So that's why I'm writing there about the MAN and WAN. NBase envisions IP as the main protocol that basically dominates today the networking environment and will improve its dominance in the following years. So this pair of Ethernet and IP is the winning combination. All other protocols installations migrate slowly towards IP. More and more installations drop basically AppleTalk or IPX, the novel network protocol, and transform their network in just IP. Even Novell and Apple now migrate from their proprietary network protocols towards IP. As you know, Novell is basically replacing their IPX protocol with IP. GFS is, of course, the NBase flagship switch, targeted for the backbone in different categories there. And I'm saying backbone because according to the bandwidth on the backplane and the support for gigabit and, of course, the number of packets per second, it is obviously a backbone device. It is a backbone that implements, as I said before, the MAN or WAN backbone, the campus and the building. And of course, in order to be able to be present on the backbone, especially the MAN, WAN, and campus, the GFS is required to have the routing capability. Routing is added as an optional capability to the existing GFS. It means we first designed the GFS, and then we saw the stringent need for adding routing. So that's why we added this routing capability in the frame processor, and it is an option. Basically, NBase decided to implement IP routing and to continue to switch or bridge all the other protocols, basically implementing a router. We continue to, of course, maintain all the powerful VLAN capabilities that were presented previously, the policy-based VLAN, custom filters, and so on, for the non-IP traffic that is switched. So you still can define a policy-based VLAN for the IPX traffic, or for the AppleTalk traffic, or for any kind of traffic that you want. You can define a trusty list and limit the IPX traffic to a certain number of workstations. The GFS IP routing capabilities position the GFS as the element of choice for backbone implementation. And in its cheaper form factors, like the 10100 with gigabit uplinks or the GFS Junior, it is a perfect candidate for departmental backbone or as a high-end segment switch. So we are trying basically to cover under this technology almost all the areas of the network up to the distribution itself. Okay, the frame processor card adds IP routing capabilities, of course at wire speed, to the GFS regardless of the port capabilities. The meaning is that today we have the gigabit Ethernet ports, and basically we are going to release very soon the 1610100 ports, and these don't support routing capabilities in the switching fabric. the routing capability is added by this frame processor card. Nevertheless, if we are going to release new port boards that are going to support the routing functionality in the switching fabric, and we are going to have in the system a mix of routing-enabled ports and routing-disabled ports, without this capability, the frame processor card will be controlled in such a way in which to add the routing capabilities just to the ports that do not have this capability. The IP routing, it is added basically in two elements of the GFS. Of course, the routing accelerator, part of the frame processor that executes the accelerated IP forwarding, and the system control CPU that runs the routing management and protocols, and of course controls the routing accelerator. I'm talking the next slides about the two elements of the routing process and how, and through this I'm going to explain how this functionality is split between the routing accelerator and the software, the system control software. Basically, a routing process has two elements, the forwarding process and the routing management process. The forwarding process simply forwards IP datagrams based on an already existing forwarding table or tables. Routing management process builds the forwarding tables and manages the information exchange with other routers, basically running the routing protocols. What is the forwarding process? In a simple manner, it's basically a datagram validation, checking the version, checking the validating the TTL, the IP checksum, and so on. Then doing basically an destination IP address resolution, search for the next hop in the routing table. And that can be extended, adding other elements like, type of service, layer 4 switching, and so on. Then, after the next hop was, the IP address of the next hop was found, it's necessary to do an IP address resolution, or ARP, that basically provides IP address to MAC address and or VLAN tag mapping. Basically, we know now to what IP entity we have to forward the datagram. We know we need the means to forward it. That means a MAC address. We have to send this to a certain host that has a certain Ethernet adapter with a MAC address. When the forwarding is done in hardware, that means that the address resolution, the ARP, needs to be already executed. That means the complex process of ARP cannot be done in hardware. So the IP to MAC, to link layer information mapping, has to be part of the routing table entry. So basically, when you're doing a search for an IP address, you're finding the next hop, and you're finding next to it, you have to find the MAC address of the next hop. Otherwise, the forwarding cannot be done in hardware. Okay, after all this address resolution, next it's the packet modification, basically changing the destination MAC address and the source MAC address, and the packet transmission on the destination port. Very simple. Now, the other part of the routing functionality is the routing management process. It first of all provides an interface, an user interface to the system configuration. IP interface configuration and maintenance, of course, IP processes configuration and maintenance, routing protocols configuration and maintenance, different human interfaces like the console, the CLI, an SNMP interface, a web-based management interface, so on. That's from the part of getting the router ready to work. So you have to configure and to maintain this. Second, the routing management process has to build and maintain the forwarding table. And that's what I explained previously. In order to execute the fast pass in hardware, you need to have for the next hop immediately the MAC address. So basically it's maintaining the IP next hop resolution table and the ARC resolution table. It also resolves special forwarding cases that can be handled in hardware, like IP broadcasts, UDP broadcast forwarding, IP options, and so on. All these special cases are handled in software. It performs the regular IP control protocols like ICMP and IGMP, the Internet Control Protocol, and multicast, Internet Group Multicast protocol. It also communicates with other routers in order to synchronize the forwarding or routing tables, implementing basically the routing protocols. And enables special switching capabilities based on the existing IP traffic. For example, and that's executing at layer 2. That's why I'm saying switching capabilities. Implements based on the IP multicast traffic and control. The switch can implement an IP multicast intelligent filtering. So the traffic is reduced. Now, what are the routing accelerator features? What are basically the GFS routing capabilities? The system, as you know, supports up to 64 ports. It can handle up to 8,000 8K IP addresses. That can be subnets, hosts, and the routing table is implemented with longest match support, basically CDIR way. Supports up to 64K routes. And that means that on average you have 4 different routes for each IP address. So basically we do support multiple routes, parallel routes to the same destination. We are ready to support type of service routing whenever it is going to be added to the standards or re-added to the standards, basically. The hardware is supporting this. It is supporting 802.1q VLAN tagging routing. That means normally one subnet is going to be mapped to a certain VLAN with a certain tag ID in the context of 802.1q. The destination subnet probably is going to have another VLAN tag. The routing accelerator and the GFS system in its routing process is able to route and at the same time to switch tag IDs. The routing rate is up to 3 million packets per second, basically limited by the GFS switching engine capabilities. You have to remember that the routing module is added as a regular port on the GFS. So basically the traffic is going first to the routing module and then back to the destination port. So basically the routing rate is about half of the switching rate. And depending on the capabilities of the switching engine, we can do probably up to 3 million packets per second in the routing module. And if we're going to improve the switching engine, that's the number that is going to be reached. It enables IGMP-based IP multicast intelligent filtering capabilities. So basically, the routing accelerator module, the hardware, it's filtering for the software all the IP multicast traffic except for the IGMP traffic. That is the control for the multicast traffic. Using this IGMP multicast control traffic, the system control software is able to install special filters at layers 2 that will minimize the influence of the multicast traffic on the unwanted interfaces. From the point of view of routing management and protocols, it supports basically all the internal area routing protocols. RIP in both versions, V1 and V2, OSPF, of course. Uses IGMP in order to implement intelligent multicast traffic reduction. Is supporting 802.1q and 802.1p in the routing context, meaning 802.1q VLAN to IP subnet mapping, what we talked before, 802.1q packet encapsulation, and 802.1p priority to type of service routing mapping. It has IGMP IP multicast intelligent filtering capabilities. We know that being on the backbone requires to be a very reliable switch and router. That's why we decided that we need to implement a virtual router redundancy protocol, that at this moment it's an IETF draft. This is something, the protocol that is pretty similar to the Cisco hot standby routing protocol, and it provides redundancy, router redundancy in the range of about 1 second, including support for static routes, and based on any underlying routing protocol. So basically the main problem in a real network is that you have a host that has a static route, to reach network I using router number 1. Now router number 1 dies, and that host cannot reach anymore that destination. The virtual router redundancy protocol provides a way out of this situation, basically providing another router that will take over the functions of the dead router with the same IP address and MAC address. So this is basically allowing to provide a redundancy in less than 1 second. It can provide in certain situations an additional level of path redundancy and load sharing. So basically by defining the static routes to go to both routers that have are redundant for each other, you can provide some level of load sharing. We also implement all the normal or standard protocols like proxy ARP, router discovery protocol, and so on. It does support a rich set of standard MIPS. The RIP V2 MIP is supported, OSPF V2 MIP, the IGMP MIP draft. We are going to have a very rich routing enterprise MIP, and so on. And that's basically going to conclude this part. That's the routing spec. It's a router, routes IP and bridges all the other protocols. Has standard routing protocol support, RIP V1 and V2, OSPF, IGMP, IRDP. Implements virtual router redundancy protocol, 8,000 IP addresses, 64K routes, 64,000 routes, multiple active routes per destination, type of service routing ready, wire speed intelligent IP multicast traffic reduction. Fully manageable with several human interfaces, the console, CLI, SNMP. It's going to be fully supported on the MegaVision NBase network management system that you're going to know probably tomorrow. And it's going to be manageable through a web-based management with both HTML and Java interfaces. Support for all the major standard routing management MIPS, the IP forwarding table MIP, RIP version 2 MIP extension, OSPF version 2, that's a mistake there, IGMP MIP draft, extensive enterprise MIP support. This should be OSPF. Just cut and paste. So basically if you have a host here, this host thinks, let's say they have a static route, they say to get, I don't know to where. I have a subnet here. To get to subnet 1, I have to go through next hop that is IP virtual. Okay? Now let's suppose this is active at this moment. handling basically the IP virtual. Now he dies. This guy is starting to respond basically to this IP virtual address that corresponds to a certain MAC address. MAC virtual. So basically, this guy takes over immediately in resolution of second or approximately this range.
Is it a standard protocol?
It's a draft. Probably it's a draft that basically it got all its numbering, so probably it's in the phase of 2-3 months being ready. It's similar to the Cisco hot standby routing protocol, just that Cisco is proprietary or it's openly published. You have to license it, but it's very similar to this. Now, in the same way, let's suppose you have you basically can do some load balancing here, because if you have another host, let's suppose you have this has MAC 2 and this has MAC 1. Okay, so if you're looking at these things, IP virtual is MAC 1, and these things that IP virtual is MAC 2. Okay, basically this guy is going to go like this, and this is going like this. So you're going to have some load sharing. You can provide also some level of load sharing through your static routes. Probably entering some. And then when the other one dies, basically this guy is going to answer to both MAC addresses. So those are the capabilities of the VRRP, Virtual Router Redundancy Protocol. Let's assume that you have 2 ports here, 1 and 2, and both are on the same IP subnet, same one. You can have, of course, multiple subnets per physical port or multiple physical ports per subnet, of course. So now you have the router inside here somehow. Now you have a host here going to host 1 to host 2. This is going to be switched. This is not going to be routed because it's the same subnet. So this is using the switching.
And the data has to be routed literally.
Of course. So if you have another subnet here, and you have host 3 here belonging to subnet 2, basically the host is going to say, okay, host 3 is on another subnet, I have to go to the router. It's going to send it to the MAC address of the router. Yes. So the switching is there. Basically, it's normally like this. It's a browser. So whatever needs to be breached or switched, it's switched. Whatever needs to be routed, it's routed. And of course, the other protocols are always switched. Performance, okay. What I was trying to explain that the capability of the routing accelerator is around 3 million packets per second. This is limited by the performance of the switching engine, because as you see here, this is first going to the router, or the port that is a router, and then goes back. Okay, so if you have 5.4 million packets per second switching, the routing is going to be divided by 2, so getting to around 2.7. As we are improving the switching capability, we are going to get probably to the 3 million packets per second. That is the capability of the routing accelerator itself. Thank you.
There are several ways to describe our data communication related fiber optics capabilities. Maybe the way I will do it is first by product categories. So here we can do one, I would say, fixed port products and The meaning of that, okay, where do I have a product where there are fiber optic ports that are fixed? So we have several switches. One 2012 FO. So this is have 8 fixed fiber optic ports. We have certain 2-port switch, almost like a bridge, like the 2001. It has an FO port, which is fixed. And we have all the gigabit products, the 3012. Currently, all the port boards for gigabits are all fiber optics. So this is one category. I will get back after that. All what I will tell you about capabilities, it will come back to these products, even if I will talk on something else. But first, I just want to go through quickly on the type of products. These are fixed port, if you can call this fixed port, because really it can be moved out from the chassis, but it's not an uplink. It's a whole port board that everything is fiber. In this case, it's 4-port gigabit, of course. The other category, which I don't even remember how many we have, is uplinks, fiber optics uplinks. So almost every product that we make, almost, I think except the 2016. Oh, I forgot here really, the 2016 FO has 2 ports of fiber, 14-port UTP, 2 ports fiber.
And 2007.
Forgot, because this one kind of killing it already.
Yeah.
With, you're right. Wow, Frank? 2007, it's FO. It's 5-port. This is much, much older product. Okay, now, fiber optic uplinks, we have many switches. We have 2 uplinks for the 2012R. Those uplinks can be fast Ethernet uplinks. So we have it for the 2012R. We have it to the 2024. I think it's maybe 4 fiber optics, not even 2. We have modules, probably 4 each for the 2032. We have module 2 uplinks, I think, for the even 228 even. So many switches have fiber optics uplinks. I cannot even try to give all the numbers, you know. But there are several types. We have fast Ethernet. Of course, we have gigabit uplink. Right now, the only product that has gigabit uplink is the 2012. We have now being released, at least beta release, is ATM. In this case, is OC3 and FDDI. Currently, this uplink is only for 2012, but it's planned for 2024 also. These two, 2012 and 2024. Okay, so that, and there are many uplinks of fast Ethernet. I don't know even how many. Too many maybe. Okay. The last category is what I call media and wavelength converters. I will write it. If I can take this off now. And here, I can call it even also extenders in some cases. It's a little bit fuzzy. So what we got here? Now we'll start to make the cross-section in a different way, which is data rate from here. And because in fixed ports, these are the data rates. I kind of covered everything. In uplinks, no, in fixed port, it's either fast Ethernet or gigabit. We have nothing else. Uplinks, I covered everything. Media converters, I will start with 10 megabit, 100 megabit, or whatever. So first 10 megabit. We don't have a big array of products, but we have some. And we are competitive in the single mode arena, not so much in the multi-mode. It's harder for us to compete, even though from time to time we are selling. So the offering in 10 megabit, the NX300 family. Why it's family? Because based on wavelength and distance, it becomes a whole family of products. So it's AUI to fiber optics. And its brother is NX301. It's UTP fiber optics. These are standalone products, available, shipping long time. For the NX301, we are working on a new form factor, and there are plans to do rack mount products also. We did some improvisation. Now we are going to be available in 4 months' time, 5 months' time, 16 racks with management for all the 10 megabit, 100 megabit, and gigabit. So I'm not writing it even, but it's planned. This is available. And here, now we talk a little bit design rules a little bit, and what are the capabilities. The multi-mode I don't want to talk about. It's standard. You can look in any other people brochure. It's about 2 kilometer distance. Maybe if you do full duplex and use some 1300 nanometer LED, we can go 5 kilometer multi-mode. But I will concentrate mostly on the single mode. And of course, single mode long distance must be full duplex. And I simply describe you a little bit the capabilities of this product in terms of distances, a little bit design rules. We have 3 main parameters to consider. One is the power out from the transmit side. Second, we have saturation power, or level. At what level the receiver of the fiber optics interface will saturate and become blind. That's usually a problem when you make them to talk too close to each other. You can have a problem. And then you have receiver sensitivity. On the 10 megabit arena, we didn't do too much work to improve what's available almost on the shelf. And we use some very simple preamp, and typically minus 29 dBm minimum sensitivity. Usually better than that, but this is what I would like to use. Saturation levels, again, it's a bit conservative, but I think minus 8. Now, as for the P out here, this is a little bit more tricky because it depends on what wavelength we are going to give that power out. And before I write down the power out, instead of that, I will emphasize a design rule that we actually didn't enforce yet in our own company, and we are going to do it now. We are in the middle of preparation of a tutorial, and we are going to teach everybody that what we are going to do in all protocols, up to, except gigabit. Gigabit is a different story. Up to 50 kilometer, we will use 1310 nanometer Fabry-Perot laser diode based products. 1310 is the wavelength. Fabry-Perot is describing the laser. Fabry-Perot laser spectrum looks like this. This is power spectrum. This is a wavelength. Looks like several modes that works, and this is the bandwidth, delta lambda, 3 nanometer. Now let's talk about this thing. Why I want to do it 50 kilometer, and beyond 50 kilometer, I want to recommend something completely different. In principle, I can do P out very high power. I can go plus 6 dBm, but this is a little bit crazy. It's issues, eye safety, other things. So let's do what's more normal. Let's say P out, let's say 0 dBm. It's a pretty good power. So how I'm going to calculate my budget link? And from that, the distance. So we have 29. The power is 0, so it doesn't contribute much. Now it's a question of how much overhead I want for the good detection. Like you have a patch panel that is not good. You have a connector that when you apply, you lose something. This is a matter of taste. But if I want to be really conservative and do really a good job, I want to put the 5. This is called overhead, okay? Then my budget link is 24 dB. So let's talk for a moment on this wavelength, 1310. What this budget link is giving me in terms of distance. And I know I took a very conservative 5 dB overhead, but that I think it's good because that prevents trouble, prevents RMAs. So what's the point? The point is, and at the moment we are talking 10 megabit, so the only consideration in all the design is power level, attenuation of the fiber. No other more complex consideration like dispersion, signal distortion because of dispersion, whatever. So it's very simple. If here this is wavelength, and this is attenuation, dB per kilometer. So at 1310, this number is 0.4, but it can vary, depends on the quality of fiber in the field, anywhere from 0.36, which I have seen some reports of very good fiber, but it can be easily 0.5 also. The question is what you are going to get. At the same time, here, simply because the wavelength is longer, so this is around 0.22, can go up to, worst case, even to 0.3, I've seen. And some people, very high quality fiber, Corning, talking about, and I have such installation to WorldCom, by the way, that we sending 106 kilometer distance, a gigabit. The guy claims that he has 0.198. But it's obvious that it's a very big difference. So if I use some numbers here to calculate here the budget link, if I use the 0.5, actually I already have a problem. It's only 48 kilometers. So if I use 0.4, 60 kilometers. So in this situation, it's quite clear that when it's approaching 50 kilometers, we have to think about something else. Now, in our nomenclature, in the way we are defining parts in the optics, there is this S1, S2, S3, all these little bit arbitrary, stupid ways of defining distances. But SX, some of this we are going to simplify, hopefully, in the next 2 weeks. But here, up to here is all 1.3 or 1310. And there is this one big jump in our cost. It's also going up very much. SZ, this 1550 single frequency laser. No. And again, we decided here almost arbitrarily that the jump will be around 50 kilometers. We must move to the SZ. And the SZ in terms of spectrum looks like this. It's 1550. Instead of having this Fabry-Perot comb, we have one mode only. This is DFB, or single frequency. And this is delta lambda. This is really not important for 10 megabit. The fact that it's one mode, it's more important for higher frequency, for dispersion. But that's the way. We didn't want to use two type of 1550 lasers. We moved to this. And if we take these numbers, let's say you take 0.25, which is very mediocre fiber, this automatically become 96 kilometers. So of course the 50 kilometers become very easy. We still can handle over 100 kilometers if customer will provide that the fiber is better than 0.2 or at least like 0.2. 0.2 will give me 120 kilometers. We can also help customers on special situation by cherry picking the optic and give, instead of 0, we can go up to +3. So this way we can break the barrier of 100 kilometers, even with this relatively poor sensitivity. But this is a story for 10 megabit. 100 megabit still will be controlled by power budget, not so much dispersion. Dispersion starts to be a problem at very, very long distance, so it's not an issue yet. I moved to 100 megabit, and we can say also 125 megabit, which will be the FDDI, and maybe even the 155 megabit, which is the uplinks of the ATM, OC3, all the same category. But in terms of media converters or wavelength converters, so we don't have many products, but we have, for example, the NX3101, which is UTP to fiber at 100 megabit. We didn't make an MI